I'm delighted, but slightly embarrassed to see that there are a number of experts in the audience. When preparing the lectures, I asked various colleagues, what level should I try to aim at? And was told that, well, probably I should aim maybe at the level of a second-year graduate student. And so for those of you who know this field very well, I think this first lecture will perhaps contain a great deal of information you already know intimately. If that's the case, please just sit back and enjoy the pleasure of recognition and feel very wise and well informed. So, of course, the course is entitled Einstein Metrics, Four-Manifolds, and Differential Topology. And the first thing I want to talk about is what's an Einstein metric. So, if you have a Riemannian manifold, a smooth manifold equipped with a Riemannian metric, then, and if you choose a base point P in the manifold, then the metric singles out a class of preferred curves called geodesics, which are locally the length minimizing curves in the manifold. And there is an associated map from the tangent space of your manifold at the base point P to the manifold. It actually might, I initially made this a dotted line to indicate that this actually might only be defined on a subset of the tangent space nearly, but it will be defined on some open neighborhood of the origin. And this exponential map, it certainly is not globally a diffeomorphism, but it is, by the inverse function theorem, it is a diffeomorphism on a neighborhood of the origin. So it will take any vector at the base point to a geodesic of the same length with the given initial direction. And if you now choose an orthonormal basis for the tangent space of the manifold at the base point, then actually this is a way of constructing preferred coordinates just determined by the orthonormal basis and the Riemannian metric. These are so-called geodesic normal coordinates, and one interesting thing you can do is then pull back the metric and say, what does it look like in these special coordinates? To lowest order, it looks exactly like the Riemannian metric, whose components would be the entries of the identity matrix. And in fact, so that's at 0th order, and even first order, the metric is exactly Euclidean, and the deviation is at the quadratic level. So only in the second order terms that you begin to perceive that your metric is not the Euclidean metric. So here, in order to simplify things, xi are the coordinates on the tangent space of the manifold at the base point relative to this orthonormal frame. And so you notice that I just defined some invariants of the metric without actually introducing any kind of technology. You can arrive at this expression for what's will turn out to be the curvature tensor R without actually first introducing the connection. These the RJ LKM here are in fact the components of the Riemann curvature tensor at the base point in the given orthonormal frame. And actually, this is essentially how Riemann invented the curvature tensor. He first defined what we now call a Riemannian manifold, and then asked, how can you change coordinates in order to simplify the local form of the metric to the greatest degree? And He didn't do it in terms of the exponential map, but he arrived at exactly this same conclusion. Of course, if you want to check my coefficients and so forth, the thing that you would want to use is that if you take a vector field on Rn that's a homogeneity 1 along radial lines, so then under this exponential map, such a vector field goes to a Jacobi field that joins geodesics through the origin, or through the base point, and they satisfy Jacobi's equation, which says that the second derivative along the geodesic of the vector field is expressible in terms of the curvature tensor. And from that, just to lowest order, just figure out what does a solution look like that vanishes at the origin and has a given first derivative. So the conventions, by the way, that I'm sneaking in here are not absolutely, no one actually agrees on what's the correct definition of the curvature tensor in terms of its sign. So just in case you're made uncomfortable about anything, the convention that I use about the curvature tensor is that the last two vectors that you put into it are the two that you are taking the covariant derivatives with. And of course, we're using the Levi-Civita connection, which is uniquely defined as a torsion-free connection, which is also metric compatible. That's to say the covariant derivative of the metric as a tensor field is 0. And these conditions uniquely characterize the Levi-Civita connection. A slightly better way of thinking about the curvature tensor, though, is that you can just take the second covariant derivative of the vector field t, and then you can, if you want, then stick in these particular vector fields u and v. The alternating part of the second covariant derivative of t is in fact the curvature tensor up to a factor of 2. And in the Penrose abstract index notation, which I'm not going to really tell you a lot about right now, this is saying that if you contract the curvature tensor with one vector field, then it's the same as taking the second covariant derivative of the vector field involved and then taking the skew part up to a factor of 2. That's this last expression, but in a different notation. All right, so if, on the other hand, like Riemann, you didn't know about covariant derivatives and so forth, and you tried to use this as the definition of the curvature tensor, you do have to impose a little bit of extra information, because you might notice that that this expression actually only determines the symmetric part in L and M, and the fact that that uniquely determines the coefficients depends upon the first Bianchi identities that R is skew in the first two indices and the last two indices, and that if you take the totally antisymmetric part in the last three indices, that you get 0. And then those can form the basis of other ways of describing the curvature tensor. So in particular, in this orthonormal frame, a component like R1212 is an example of a sectional curvature. So the sectional curvature, which is not going to be one of the fixations of this particular set of lectures, but it's important to know what it is. It's a sectional curvature is a function on the Grassmannian of two planes in the tangent spaces of the manifold. So, so at each point you have a Grassmannian of two planes in that tangent space, and now you can assemble the union of all such things into a bundle over the manifold, and the sectional curvature is a function of that bundle, and it compares distances by the exponential map. It compares distances to the Euclidean answer. So if you have a narrow isosceles triangle, you then spray it out into the manifold via the exponential map and ask what is the distance between the two base points relative to the Riemannian metric. Then you would find, in the spirit of the previous statements, that, well, if you divide by the Euclidean answer, it looks like 1 minus something of order epsilon squared, where epsilon is the length of the sides here, and the coefficient is the sectional curvature of this plane. So it's particularly worth noting that if the sectional curvature is positive, that the distance would be less than you would expect from the Euclidean model. And if the sectional curvature is negative, it would be more. Of course, this whole discussion is assuming that the angle is very small. It becomes more complicated otherwise. So in particular, one of the basic facts, going back, I think probably to A.D. Cartan, is that the sectional curvature of a Riemannian of a complete compact Riemannian manifold is 1, and if the manifold is simply connected, then in fact it is diffeomorphic to the standard sphere, but it's actually, the metric is isometric to the standard metric. So knowing the sectional curvature actually characterizes the standard metric on the n-sphere. Now, Ricci curvature is not fundamentally the study of distances. It's about the study of volumes. If in these same geodesic normal coordinates we ask, well, what does the volume form or the volume measure of the manifold, of the Riemannian manifold look like compared to the Euclidean one? To lowest order, they are actually the same, and then there's a quadratic deviation, and they're higher order terms. So here, I mean, there is some function here, I'm just describing its Taylor expansion. The quadratic terms define a certain symmetric quadratic form on the tangent space at the base point, and that's exactly the Ricci tensor. All right, so Ricci did not discover the Ricci tensor in this way, and that's why the coefficient here is minus 1/6 and not 1. But actually, when you're trying to conceptually understand what is the Ricci tensor, what is it all about, it has to do with volume comparison. So in order, if you want to deduce this little formula as a nice exercise, remember that the metric volume form looks like the square root of the determinant of the matrix of metric coefficients in the given coordinate system. And so here, if you so the previous expression is interpreting d mu as a form. Certainly you don't want to do that on an unoriented manifold, but there's perfectly well-defined volume measure. You just take the absolute value of the top form, if you like. The metric becomes in these coordinates we've already said, it's the Euclidean metric plus a certain quadratic deviation, which is determined by the curvature tensor. And when you now when you say, well, the determinant of the identity matrix plus epsilon times another matrix, the lowest order term involves the trace of that matrix, and so there's a slight variation. If you take the square root, it just changes the coefficient to a half. And that's why this goes from being minus a third to being minus a sixth. All right, so the Ricci tensor is this fundamental gadget that measures, that kind of plays a fundamental role in understanding the comparison of volumes in your Riemannian manifold to volumes in Euclidean space. It's worth noting that, so here, this is just a very rough universal statement at lowest order. There are some deeper and very interesting comparisons which you can make at finite distance rather than imagining you're taking only small distances from the base point, and the most important of those is the Bishop-Gromov inequality, which gives you a lower bound for given a lower bound for Ricci, you get an upper bound for volumes. All right, so the Ricci curvature is by definition a function on the unit tangent bundle. So on the set of tangent vectors on the manifold of unit length, one can look at the function which takes any unit vector to the number given by contracting two copies of it with the Ricci tensor. And if you like, more conceptually, this Ricci curvature function is one which is really comparing if you take a small open set around a given unit vector in the unit sphere, and then you take the cone on that up to some distance epsilon, and take its image under the exponential map, then the volume of the answer divided by what you would expect in Euclidean space will look like, well, up to lowest order it will look like 1, and then there's a quadratic deviation, and the coefficient here is the Ricci curvature. It comes in with a minus sign, and then there is a nuisance coefficient depending upon dimension, n over 6 times n plus 2, that reflects the fact that this is not how Ricci invented the Ricci tensor. He instead just found out that it was a really nice algebraic device to get something simpler than the curvature tensor, which in low dimensions contains a lot of the information of the curvature tensor. So of course you can do this at near any unit vector, take any sufficiently small neighborhood of that vector in the unit sphere, and then you can truncate the cone at distance epsilon from P. All right, so for example, with this definition, you find that if you took the unit sphere in Euclidean space, unit n sphere in Euclidean n plus 1 space with its induced Riemannian metric, then its Ricci curvature will turn out to be n minus 1. Identically, the function on the unit tangent bundle is identically n minus 1. But if the dimension n is bigger than or equal to 4, unlike the sectional curvature, this geometric condition is not enough information to characterize the metric. All right, so we've just pointed out that it's interesting to look at. We've just seen a very simple example of a manifold of constant Ricci curvature. Take the unit n sphere, or more generally, take the round n sphere of any radius in Euclidean space, and that will have constant Ricci curvature. And on the other hand, this condition, because we're requiring this, that for every unit vector with respect to G, R of VV will be a particular constant lambda, this is equivalent to saying that the Ricci tensor is exactly lambda times the metric. And so that is an equivalent reformulation of the condition of being an Einstein metric. Now, Einstein, well, he was a physicist. This is some kind of terminology that has something to do with physics. Physicists would not call this, they don't usually call solutions of this equation Einstein manifolds. What they would say is that this equation is the Einstein vacuum equation with cosmological constant, where lambda is the cosmological constant. However, in physics, the metric G, which we're always taking to be positive definite, would usually be indefinite. And in the case studied by Einstein, it would have been in dimension 4, where we would have something like Lorentz signature that would, let's say, be 1 negative direction and 3 positive directions. But nonetheless, the source of this particular equation is linked to physics. So I'll now ask my expert friends in the audience, why do we call the metric G? You pick up a random book on differential geometry, Riemannian metric is usually called G. Why do we call it G? It's Einstein's notation. For Einstein, G meant the gravitational field. So somehow there is a historical link to physics here. But on the other hand, what did Einstein think about this equation? In fact, he called it the greatest blunder of his life in a conversation with George Gamow. And here's a picture of him around 1930, where he's definitely thinking that, well, he really wishes he had never mentioned the possibility that in empty space, the Ricci curvature might be anything other than 0. So as punishment, mathematicians call lambda the Einstein constant. It has the same sign as another form of curvature I haven't mentioned yet. The scalar curvature is, by definition, the trace of the Ricci tensor, or that's the full trace of the curvature tensor. And the scalar curvature for an Einstein n-manifold would actually be n times the constant lambda. So in particular, the scalar curvature, and for an Einstein manifold, the scalar curvature has the same sign as the Einstein constant. Again, in terms of an elementary, having some elementary pictures in your head about notions like scalar curvature, you can think of the scalar curvature as being you measure the volume of a ball of radius epsilon in the manifold, where epsilon is, let's just say, the distance ball, we define with respect to the Riemannian distance, divide by the answer in Euclidean space, and then which is a certain constant, which I haven't written out, depending upon n, and then the lowest order, the answer is 1, then there's a quadratic deviation, and then there are things of higher order. All right, so for example, having positive scalar curvature, it would imply that a sufficiently small ball would have smaller volume than it would have in Euclidean space. It turns out, by the way, a very hot topic even now in research in Riemannian geometry is to try to understand obstructions to having positive scalar curvature on a manifold. And you might think that this looks like a synthetic explanation of what the scalar curvature means, but it has the shortcoming that, here we're taking the Taylor series expansion. A priori, this is true for sufficiently tiny epsilon. When epsilon is any ponderable size, you tend to have no control on volumes, just knowing the scalar curvature. And so people like Gromov have been spending a lot of time trying to find a better synthetic interpretation of the scalar curvature. All right, so a Riemannian metric is said to be Einstein if it has constant Ricci curvature, or the Ricci curvature is lambda times the metric. This equation is rather nice because, for example, just on the level of PDE, it generalizes the constant sectional curvature condition, but it's actually usually weaker. Turns out to be equivalent to constant sectional curvature in dimensions 2 or 3, but once you get to dimension 4, it's strictly weaker. In any case, even locally, this is a determined system of PDE. If you've chosen lambda, then this is, and you look at this equation, well, the components of the Ricci curvature involve second derivatives of the metric, and you're saying that system of second order expressions is the same as lambda times the metric. Here, the number of components of the Ricci tensor is the same as the number of components of the metric, and so people in PDE would say this is a determined system. It's actually still not a very good system if you don't introduce some other ideas. You might notice that actually the curvature tensor, by contrast, has more independent components. The number of independent components grows chordically rather than quadratically, and it's a nice exercise to count these exactly. The real observation is that the curvature tensor is exactly characterized by the Bianchi identities by saying it is in the second, it's in the symmetric square of the two forms, and is in the orthogonal complement of the four forms. Or a different way of saying that is if you now project to the quotient symmetric square of the two forms modulo the four forms, and notice that the four forms are in the symmetric square of the two forms, right? Because it's a symmetric operation when you wedge together two forms. So it turns out that the curvature tensor actually ranges freely over this space, and that's its dimension. A nice little exercise to the combinatorics. All right. So if we don't, an essential feature of the Einstein equations is that they're invariant under diffeomorphisms. If you pull back an Einstein metric by a diffeomorphism, it is still an Einstein metric because the Ricci tensor pulls back. The pullback of the Ricci tensor is also the Ricci tensor of the pullback metric. So that certainly can't be elliptic. They're going to be, the space of solutions naively is infinite dimensional. It doesn't behave like an elliptic equation. But one thing you can do is say, well, you're allowed to specify what kind of coordinates you look at the metric in. You can impose the condition that you're in harmonic coordinates. Ask that with respect to the given metric, each coordinate is a harmonic function. And then in terms of, in such a coordinate system, it turns out the Ricci tensor, component by component, is the same as half of the components of the metric. Now take the Laplacian of the components of the metric as functions, and then there are lower order terms. I've denoted those by LOTS because there are lots of them. So here, analysts in the audience may be unhappy with the sign of the Laplacian that I use, and this is true of a very large segment of the differential geometric community. For many of us, the Laplacian is the same as the Hodge Laplacian on functions, and that's the same as minus the trace of the Hessian rather than the trace of the Hessian. And so a piece of good advice for young and old in this subject is when you read a paper in differential geometry and there's an expression involving the Laplacian, if it's an author that writes carefully, they'll tell you what the sign of that is the first time they use it. But otherwise, look at it carefully, and sometimes if they're being careless, they're changing sign conventions all over the place, which can lead to major mistakes in proofs. So, sign of the Laplacian, something to pay attention to. All right, so one little algebraic fact which I will use later on. You might notice that this condition on the Ricci tensor, it says that it is a multiple of the metric, and in particular that means the trace-free piece of the Ricci tensor vanishes. But if you were merely to say, well, the trace-free Ricci tensor vanishes, a priori what that is saying is that the Ricci tensor is some function times the metric. However, if your dimension is not 2, if you're in at least dimension 3, it turns out that the condition that the trace-free Ricci tensor vanishes is the same as saying that you have an Einstein metric. The difference is that here, so it's important when you say something is Einstein, without any other information, you haven't specified what the Einstein constant lambda is. And this, when I say it, this implies the Einstein, this is equivalent to the Einstein equations if you're in a dimension at least 3. That fact, of course, is you don't know what the value of lambda is. So this condition, having trace-free, the vanishing of the trace-free piece of the Ricci tensor is equivalent to having this satisfied for some constant lambda. So because I assume that, and I'm hoping that I'm right, that there's a significant contingent of this audience consisting of students, let me give you some proofs of simple facts like that, which I think are important. So first of all, how do we think of the curvature tensor? The curvature tensor, the curvature of any bundle should be thought of as a 2-form with values in some bundle. If it's a connection on a bundle E, it's a 2-form with values in endomorphisms of the vector bundle E. In this case, the vector bundle in question is the tangent bundle. So it's a general fact called the differential Bianchi identity, or sometimes called the second Bianchi identity, is that when you think of it in this way, that 2-form is a closed 2-form. When you take the exterior derivative to get a 3-form with values in a bundle. Now the problem is that the usual Durand D only makes sense on ordinary 2-forms. Here you have a bundle value 2 form, and you have to lift that operator to act on bundle value 2 forms, and that involves the connection. Literally, this condition could be written out in terms of either components, or the way I think of it is in the abstract index condition. If you follow the abstract index convention, that's simply thinking of each index as saying this is a tensor with these slots. And unlike it's very useful to have a label on each slot. It's like having an address on each mailbox. So if you're trying to take a collection of vectors and stick them into the tensor, you know which one goes in which place. All right, so here, if we take the covariant derivative of the curvature tensor and we take its Q part over the first 3 indices, then that vanishes. And that's equivalent in a less elegant way. This is really the same as saying that if you take the cyclic sum over the first 3 indices, so sum over cyclic permutations, you get 0. Now what you can then do is raise 2 of the indices, and then contract. So take these 2 indices to be actually the same as this pair of indices. When you do that, then actually the first term is the derivative of the scalar curvature, and the other 2 terms, up to sine, turn out to be the divergences of the Ricci tensor. In other words, this is the same. The divergence of the Ricci tensor is half of the exterior derivative of the scalar curvature. This has nothing to do with any equation. It's just for any Riemannian metric, this fact is true. The divergence of its Ricci tensor is half of the exterior derivative of the scalar curvature. And if you really hate indices, you might try to abbreviate it in this way. However, let's put the indices back in and look at what we get when we take the trace-free piece of the Ricci tensor. What is its divergence? Well, the first thing has divergence, which is half of the derivative of the scalar curvature, and then just almost by it's a tautology, that the divergence of this just would lower that index b. So you end up with just minus 1 over n times the scalar curvature. So now you notice that there's something weird about dimension 2. If n is 2, this vanishes. You haven't learned anything. But if n is not 2, then if n is not 2, and you assume that the trace-free piece of the Ricci tensor is 0, then you immediately would find that the derivative of the scalar curvature is 0, and so assuming the manifold is connected, this says that the scalar curvature is constant. Now, of course, that goes back to then plugging in that S is constant, and now defining lambda to be the scalar curvature divided by the dimension. You go back and you find this is actually predicting that you have that your metric is actually a solution of this Einstein equation. Little warning, by contrast, in dimension 2, the story is completely different. In dimension 2, the entire curvature tensor is determined by one function, usually called the Gauss curvature, but it's the same as the sectional curvature of the surface in the only 2 plane that it has in its tangent space. And it'll turn out that in dimension 2, that Gauss curvature completely determines the Ricci tensor. The Ricci tensor is always the Gauss curvature times the metric, and so in particular, that says that in dimension 2, the trace-free Ricci tensor always vanishes. But on the other hand, on a generic Riemannian surface, the Gauss curvature will not be constant, and therefore, that's not considered a solution of the Einstein equations, where we have strongly put in that lambda is supposed to be a constant. All right, so what are the main questions that are going to concern us in these lectures? The first is the existence question. Which smooth compact N-manifolds admit Einstein metrics? In dimension 4, there are obstructions which have no known analog in other dimensions. And we will meet the first of these in the second part of the lecture. But we will also discuss many existence results where we'll see interesting classes of four-manifolds do admit Einstein metrics. And in the best of circumstances, it'll turn out that these non-existent statements and existent statements are essentially complementary. So there will be classes of manifolds where we'll be able to tell exactly which of them admit Einstein metrics. So, oops, jumped too far forward. So the other main question one would like to investigate is, so I've been talking, the first question was an existence question, and you're usually interested in existence and uniqueness questions in mathematics. So in addition to existence, we could ask about uniqueness. When there is an Einstein metric on a given manifold, how many of them are there? It turns out the answer to, there's no simple general answer to this question. It's quite subtle and interesting. But if you phrase this, if you interpret this in the most naive way, this is almost a silly question. And the reason is that if you were just saying how many metrics with this property are there, there would automatically, if there's one, there's an infinite dimensional space of them. So if you have an Einstein metric and you have any diffeomorphism, then as I've previously observed, the pullback of an Einstein metric via a diffeomorphism is also Einstein. And so, well, on any manifold, there will be an infinite dimensional space of diffeomorphisms. In particular, you can look at the flows of vector fields for small times, and so that depends on infinitely many parameters. So the diffeomorphism group is always infinite dimensional, and it would the isometry groups of Riemannian manifolds are always finite dimensional. So this is a way you would automatically know that there would be an infinite dimensional space of other solutions of this Einstein equation, given just one solution. Of course, if you're thinking about this in the right way from the viewpoint of Riemannian geometry, you're not interested in questions that are about the appearance of a metric in a particular coordinate system, so you would automatically see from the start that a manifold with a metric and then the same manifold with the metric pulled back by a diffeomorphism, those are isometric. So the given diffeomorphism is an isometry between those Riemannian manifolds. And so these two objects are really thought of as the same from the point of view of Riemannian geometry. So there's another cheap trick that you can use to go from having one Einstein metric to having more of them. This does not involve quite so much flexibility, but if you multiply an Einstein metric by a positive constant, that new Riemannian metric will turn out to be Einstein. So the point is that in general, if you take any metric and you multiply it by a constant, that does not change the Riemannian connection. So the reason I beat a dead horse by reminding you of the conditions to characterize the Riemannian connection, the Levi-Cheeta connection, it's that it's a torsion-free connection and the covariant derivative of the metric is 0. But that means that actually if you multiply the metric by c times the metric also has covariant derivative 0, so it must have the same Levi-Cheeta connection. So multiplying a metric by a constant does not change the Riemannian connection or Levi-Cheeta connection, and therefore it does not change the curvature tensor, because the curvature tensor is directly defined in terms of the connection. Here, when I say this, of course, there are circumstances that in Riemannian geometry sometimes people confuse the curvature tensor with with lowering one index, so it becomes something that eats 4 vectors rather than eating 3 vectors in a 1 form. If it's something that eats 3 vectors in a 1 form, that's unchanged when you multiply the metric by a constant. And the trace that you use to define the Ricci tensor does not involve the metric directly. So when you multiply any Riemannian metric by a constant, the Ricci tensor does not change. And I know good geometers who get confused about this, because if you're interested in the Ricci curvature, which is this function, take the Ricci tensor and evaluate it on unit vectors, that changes because the notion of a unit vector has changed. But the tensor is left the same. All right, so if G is an Einstein metric with Einstein constant lambda, and then you define a new metric by multiplying the metric by a positive constant C, then the new metric is also Einstein. It's simply that the Einstein constant is now C inverse times the original Einstein constant. Oh, so here I should have broken this next slide up. I didn't. In order to make this uniqueness kind of question, or the best approximation of uniqueness question that's at all interesting, one really should not consider particular Einstein metrics, but rather equivalence classes of Einstein metrics under these operations. Pull back metrics by diffeomorphisms, multiply Einstein metrics by positive constants. And so there's a group, the diffeomorphism group of the manifold, and the multiplicative group of positive real numbers. This group, the Cartesian product, acts naturally on the set of Einstein metrics, and the quotient is called the Einstein moduli space. And so the interesting question that's in the direction of uniqueness would be about what kind of structure does this Einstein moduli space have. It's not clear from the definition I've given that this, so as it's described, it certainly has a quotient topology. It's not clear, obviously, that topology is very nice. It turns out that this is a metrizable space, and it has an induced distance, one of which is, one way of metrizing it is using the Gromov-Hausdorff distance. But anyway, this moduli space has in particular, it is a Hausdorff topological space. You could ask, for example, is it connected? If you have two, is it connected? Is it path connected, and so forth? Is this space, this Einstein moduli space, is it discrete? Is it perhaps just a point? Or is it, say, a manifold of some positive dimension? It turns out that in order to get precise answers for these kinds of questions, the answers turn out to strongly depend on the dimension, and that dimension 4, we'll see that the types of answers one gets are quite different from the kinds of answers one gets in higher dimensions. And what I hope that you'll come away with from these lectures by concluding that the study of Einstein moduli spaces is quite fascinating, but also that it is different in dimension 4 than it would be in higher dimensions. And at that, I'm going to now pause for a coffee break. And so thank you for your attention. I was actually thinking I would go on a little bit longer, but this is a good place to take our first pause. I'm sorry that I went a little bit fast during the first part of the lecture, and the reason was that I was really afraid, seeing some of my distinguished senior colleagues here, I didn't want to bore them too much, but after all, I'm trying to make this an accessible area for younger people. So before I recommence, are there things that you would like me to back up and explain more about things I've already said? I can certainly go back and clarify certain points if that would be useful.
I have a question of this diagrams about the existence of the global diffeomorphism group.
Oh, yes.
You explain how to get about it.
Okay, so the key basic point is that when you're on, let's keep it simple because I'm discussing compact manifolds without boundary. So on a compact manifold with boundary, if you take any smooth vector field, there is a well-defined one-parameter group of diffeomorphisms generated by the vector field. Okay, and so that automatically tells you, so actually even on a non-compact manifold, you can use almost the same trick. If you take any compactly supported smooth vector field, it then following that vector field, it generates a well-defined global group of diffeomorphisms, one-parameter group. If you don't put in the condition that the vector field has compact support, it's more complicated because following a flow line, you can basically fall off the edge of your little universe. Right? But if it's compactly supported, that doesn't happen. Anyway, so certainly on an arbitrary manifold, the space of smooth, and of course we're always working in dimension at least 2 for any of this discussion because you can't do Riemannian geometry in lower dimensions. So the space of vector fields on a manifold, even in dimension 1, but at any higher dimension, there's an infinite dimensional space of vector fields, and they generate they generate an infinite dimensional diffeomorphism group. There is one subtle point. The naive way of thinking about it is that the space of vector fields, the space of smooth vector fields on your compact manifold is the tangent space of this infinite dimensional Lie group of the diffeomorphism group of the manifold. However, there's a subtle point. If you have a diffeomorphism that is close to the identity, it may not be given exactly by the flow of a single vector field. If you allow your vector field to be also time dependent, you can get any nearby. If you have a diffeomorphism, self-diffeomorphism of the manifold that's near the identity, you can always think of it as gotten by taking a path in the vector fields and then integrating this time-dependent vector field. But still, morally speaking, it's okay to think that the space of the smooth vector fields on your manifold is the tangent space of this infinite dimensional group of diffeomorphisms. And in particular, my real point was that the diffeomorphism group is definitely something infinite dimensional. Its size is like the space of smooth vector fields. That's something infinite dimensional. All right, so the other general fact that that many of you are aware of, but if you haven't been thinking about Riemannian geometry very long, you might not know that the isometry group of a smooth compact Riemannian manifold is necessarily finite dimensional, and there's even a dimension estimate. It's no bigger than the isometry group of the insphere. So in fact, it's the maximum dimension that you can have in dimension n is n times n plus 1 over 2. So it doesn't matter what the number is, but there's an a priori upper bound. So you have, whenever you take a particular metric and you move it around via diffeomorphisms, you're going to generate some huge infinite dimensional class of different metrics, which are nonetheless morally actually the same metric. In particular, I mentioned briefly that there's a Gromov-Hausdorff distance between two compact metric spaces. It turns out that there, from the point of view of the Gromov-Hausdorff distance, these changing the coordinates, if you like, moving your metric via diffeomorphisms, you're not changing the metric space at all. Two things that are isometric, and the Gromov-Hausdorff distance between them is actually 0. Okay, is there other questions? Or I can, in particular, if there are any slides you'd like to see again, I can go back and go over those points. Yes.
I would like to know if the picture changed a lot if you consider a pseudo-Riemannian manifold, or it's more or less the same so far.
if you can, semi-Riemannian manifolds or pseudo-Riemannian manifolds, some of us say. Yes, so this is a natural question because after all, as I emphasized, the origin of the Einstein condition is really in physics, and Einstein was really interested in Lorentzian metrics in dimension 4, and in physics today, people often spend part of their time discussing metrics of Lorentz signature, even maybe not in dimension 4, could be of something higher dimension. The essential thing that's, it turns out that when you study Einstein's equations for Lorentz metrics or pseudo-Riemannian metrics, you're usually doing it on non-compact manifolds. So in the context of physics, one usually studies something like the initial. So actually, we're in a theater that's named for Yvonne Choquet-Drouin, who in her thesis made a very, very important contribution to relativity by showing that the initial value problem for Einstein's equations, for example, the Einstein vacuum equation, but with the cosmological constant lambda, the story would be the same. This is a well-posed problem in hyperbolic PDE. But in that context, the space of solutions is always infinite dimensional. You can choose different initial data, and what you're trying to show is that, there's a consistency condition on the initial data, but given an initial data set, then you can produce solutions of Einstein's equations with that initial data. So you'll always have an infinite dimensional space of solutions. Here, we're looking at the Riemannian metrics that satisfy the Einstein condition on a smooth compact manifold without boundary. And by the way, so I didn't explicitly say in the slides, without boundary, what's the definition of a manifold? A manifold with boundary is actually not a manifold by the naive definition. It's not locally Euclidean at the boundary. There's something called a manifold with boundary, hyphenated term, right? When I say manifold, I mean something which is locally Euclidean. Compact manifolds are implicitly always also compact without boundary. Okay? That's the context where we're looking for Einstein metrics. It'll turn out that each component of the moduli space turns out to be finite dimensional in that context. So you never have solutions that depend on infinitely many parameters. But that's in the sense of saying the moduli space. The components of the moduli space are finite dimensional. But there's no analog of that theorem in the context of pseudo-Riemannian metrics. You might say, well, let's just, as a mathematical game, forget what the physicists want to do, let's look at indefinite metrics on a compact manifold and say, is there any kind of theorem about finite dimensionality? It turns out that the answer is no. So for example, on the 4 torus, there's an infinite dimensional space of solutions of the condition of having Ricci tensor 0, so that's Einstein with lambda equal to 0. Among those metrics of signature 2, 2 positive directions, 2 negative directions. One of my students, Jimmy Patian, showed right after his thesis that on the 4 torus there are infinite dimensional families of solutions. So somehow the real point is that there was a certain point when I said that if you looked at Einstein's equations in harmonic coordinates, then the equation, the local form of the equation is that it is an elliptic equation. So that's a kind of local statement, but there are global versions of this gauge condition that you can impose. You can ask that the identity map from some background metric to the given Riemannian metric, the solution of the Einstein equation. Ask that map be a harmonic map. That's a generalization of this harmonic coordinate condition. It turns out that you can use that So for Riemannian metrics, that makes the equation elliptic, and it makes the moduli spaces finite dimensional. So the finite dimensionality is a distant generalization of the fact that when you look at eigenspaces for the Laplacian on a compact manifold, that the eigenspaces are always finite dimensional. So if by contrast you're working with if it's a Lorentz metric, the corresponding statement about the system would be that it's a hyperbolic equation. It's like the wave equation. And if instead you have, let's say, two positive directions, two negative directions on a four-manifold, that's sometimes called split signature or neutral signature, if in that setting the equation becomes ultra-hyperbolic, and you have all of these phenomena that are generalizations of the fact that when you're solving the wave equation, you tend to get an infinite dimensional space of solutions rather than a finite dimensional space.
Thank you.
Other questions? If not, I will then proceed with the second part of the lecture, and I'll try to avoid the temptation to speed up too much. Let's see. There's my pointer. Oh, thanks. All right, so in the first part of the lecture, we met the definition of an Einstein metric. It's one of constant Ricci curvature. And I now want to point out how, depending upon the dimension of the manifold you're looking at, the character of the solutions will vary wildly. So if you are in dimension 3 or in dimension 2, then Einstein's equations actually become locally trivial in the sense that any Einstein metric in these dimensions, it turns out that in low dimensions, in dimension 3, dimension 2, if you know the Ricci tensor, you can then deduce the structure of the entire curvature tensor. So if you wanted to just look at the count of components I gave you before, about how many components does the Ricci tensor have, how many independent components of does the curvature tensor have, then, for example, in dimension 3, it turns out that there are 6 components, and that for either, right? So, and in fact, there's an algorithm for concretely determining the curvature tensor from the Ricci tensor. The real point is that in dimension 3, the star operator says that two forms are essentially the same as vectors. And you can think of the curvature tensor as being something in the symmetric square of the two forms in general, but that means in dimension 3, it's the same, it's in the symmetric square of the tangent bundle. So it has the same number of components as the Ricci tensor. The algorithm is a little more complicated than you might think. You have to throw in a certain multiple of the identity depending on the scalar curvature to actually get from one picture to the other. But in dimension 3, the Ricci tensor determines the curvature tensor. Constant Ricci curvature implies constant sectional curvature. What does a manifold of constant sectional curvature look like? If you assume that the manifold is complete, then it really goes back to Eddy Carton, that the universal cover is either the standard sphere or Euclidean space or hyperbolic space, may be changed by homothety. Maybe you multiply those standard metrics by a constant. Those are the only models for the universal cover of an Einstein manifold in dimension 3, similarly in dimension 2. So in these low dimensions, a An Einstein metric is simply a metric of constant sectional curvature, and this turns out to be very useful. It's really the basis of the Ricci flow proof of the Poincare conjecture. You're starting with something that smells like it should be the three-sphere, and you want to flow to get to a metric that has constant Ricci curvature. It's quite complicated because there are all kinds of pathologies that happen where the metric, under the Ricci flow, the metric can blow up. You have to keep performing surgeries. But the proof of the Poincare conjecture, following Hamilton and Perlman, is based on the fact that constant Ricci curvature in dimension 3 is the same as constant sectional curvature. So in these low dimensions, it's not that these metrics are not interesting. Constant sectional curvature metrics actually, while they're locally trivial, globally, there's a lot to say. But it's not, the point is that the theory of Einstein metrics devolves into something very locally, very trivial, globally perhaps more complicated in these low dimensions. What about, what happens if the dimension of the manifold is high? And by high, what I mean is the dimension is at least 5. It turns out in differential topology, there was a breakthrough made by Smale, which ended up saying that for high dimensional manifolds can be completely understood in terms of surgery theory. And really, high dimensional manifolds, their differential topology turned out to be easier to understand than the differential topology of four-manifolds. In dimension greater than or equal to 5, but when you're just saying, start with some very familiar manifold, what can you say about the moduli space? So I mentioned the Poincare conjecture in dimension 3 a moment ago, and the strategy there is to try to show you have something that you suspect might be the three-sphere. Say it's a simply connected, smooth 3-manifold. You try to show that it has an Einstein metric on it, and that Einstein metric actually has constant sectional curvature, and then it's sort of then a classical theorem of Élie-Cartan. It would have to be the standard three-sphere with the standard metric. Right? That was the underlying motivation for the whole Ricci flow program. What happens in dimension 5 or greater, though? Suppose you have something which you suspect is the 5-sphere, and you say, here's an Einstein metric on it. Can I tell whether it's the 5-sphere or not? Well, the problem is that the 5-sphere has lots and lots of non-standard Einstein metrics. The moduli space of Einstein metrics on the 5-sphere turns out to have infinitely many different connected components. If I give you one of these metrics, I give you an Einstein metric on the sphere, and you here, look at this thing under a microscope. Is this manifold the 5-sphere? Well, typically, you're looking at some Einstein metric which is very, very unlike the standard Brown metric, but you can't deduce from its local structure that the manifold you're looking at is the standard 5-sphere, because it's the 5-sphere equipped with some very unfamiliar Einstein metric. And by the way, I should say, we do not know how to understand the generic Einstein metric in any dimension right now. What we usually do when we're trying to prove existence, we impose some extra conditions. On the 5-sphere, the original proof of this for the 5-sphere was due to Christoph Böhm, who showed that when you look at metrics on the 5-sphere that have very large isometry groups, these are the isometry group. These are metrics of homogeneity 1, so the isometry group is not acting transitively on the sphere, but it acts transitively on a family of hypersurfaces for some particular family of hypersurfaces in the 5-sphere. What Böhm was able to show was that on the 5-sphere, you could find a sequence of Einstein metrics with, let's say, the fixed Einstein constant, maybe lambda equals 4, but where the total volume of the metric went to 0. It turns out on each connected component, that volume would be constant. That's related to the Einstein-Hilbert variational formula, which I'll say something about later in the lectures. So actually, this theorem is not just about S5, and this is actually true of any odd-dimensional sphere. There was a different proof of the same fact for the phi sphere, which was done by Tristan Collins and Gabor Zeki-Lahidi, who showed that rather than looking at metrics with large isometry groups, they looked at the so-called Sasaki-Einstein metrics. And the Sasaki-Einstein metrics, you still have at least a one-dimensional isometry group, but generically you might not have any more isometries. So there's only, these are metrics, the ones they studied have circle actions, but maybe nothing else. So they reproved this theorem for this very special class of Einstein metrics. And then more recently, this proof has been generalized by several different groups of people to any odd-dimensional sphere. I should have names of those groups. But anyway, this is a strategy. Böhm's method cuts off. Böhm does get a lot of even-dimensional cases, but his method turns out to kind of stop at dimension 10, whereas for the proof of Collins and Zeki-Lahidi can actually be generalized to higher dimensions. Another an example of the fact that moduli spaces of Einstein metrics might not be connected. It turns out that so if you for example fix the volume, you only look at metrics of total volume 1, then the Einstein constant is constant on each connected component of the moduli space. But starting, the lowest dimensional examples that are known of this phenomenon so far are in dimension 8. There are smooth, compact 8 manifolds that admit pairs of Einstein metrics where lambda is positive for one and lambda is negative for the other. So they're certainly in different connected components of the moduli space. So it's significant here. The method, this was something that I did with Fabrizio Catanese. Our method really depends upon that 8 is 2 times 4. So we actually discovered this because it's related to a certain phenomenon in dimension 4. And 2 of my students, Radosh Rasteitanu and Ioana Shuvaina, it's a married couple, who also are mathematical collaborators sometimes, they've discovered a generalization, a very beautiful set of generalizations of our argument where they showed that actually, so we had like one example in dimension 8, and then they found a large family of them, and you go up in dimensions that are multiples of 4, and you get huge numbers of solutions. All right, so somehow in high dimensions, the Einstein condition allows for a huge amount of flexibility. You should not, if you have a very standard manifold, and you say, I have an Einstein metric on it, why would that Einstein metric be one of the familiar ones? Even if something like a sphere where you know a standard Einstein metric on it, you could find a solution of the Einstein equation, and it might be something completely different from what you expected. There are probably, if you like, there are too many solutions. Yes?
A detailed question on the first one. In physics, you fix lambda.
Yeah.
But here in moduli space, it's for all lambdas together. Right?
Yes, that's
one
right.
equation.
Yes, that's right.
So why is it better?
Well, if you like, it's a different question.
Sure.
So I will discuss. So for with the conventions I've been describing, one usually allows lambda to vary, but if you multiply an Einstein metric by a constant, then that does change lambda, but it never changes its sign. So, and it turns out, in particular, therefore, for And you can make more refined things, look at representatives of total volume 1, then it turns out that the value of lambda is related to a very nice invariant of Riemannian metrics. But so one of the interesting questions that I'll want to discuss is this question about to what degree is the sign of lambda determined by the differential topology? If you're looking at something like in dimension 3, where you know that an Einstein metric has constant sectional curvature, then actually the sign of that sectional curvature is related to the size of the fundamental group. If you have something with positive sectional curvature, even positive Ricci curvature, the fundamental group must be finite. Whereas for something like a hyperbolic manifold, when you have something of negative sectional curvature, then its universal cover would necessarily, its universal cover would be a negatively curved complete manifold, simply connected. It would have to be hyperbolic space, or if lambda is 0, it would have to be Euclidean space. And that means if the quotient, if the original manifold is compact, that can only happen if the fundamental group is infinite. All right. So the size of the fundamental group is sort of helps you determine in dimension 3 what the sign of lambda would be. We'll see this is not true at all in dimension 4. Lambda can be negative on a compact simply connected format. All right, so for me, I think of 4 dimensions as the Goldilocks zone for Einstein metrics. Now, if you didn't grow up hearing the standard fairy tales that are told to children in the English-speaking world, you may not know who Goldilocks is. Goldilocks and the Three Bears is a story for children about a little girl who breaks into a house in the middle of the forest and finds very nice things there, bowls of soup, big chairs, beds, and so forth, and tries them all out. Not realizing that the owners of this house is a family of bears who eventually come back. Goldilocks and the three bears. And so in the English-speaking world, there's this term, the Goldilocks zone, because in each case, Goldilocks tries out, for example, the chairs. This one is too hard. This one is too soft. This one is just right. Tries out the soup. This one is too hot. This one is too cold. This one is just right. Now, actually, the first people that lifted this term, that created the term the Goldilocks zone. So here the point is that in dimension 4, the Einstein condition is not too rigid, it's not too flexible, it's just right. And this term, the Goldilocks zone, was first used in the study of exoplanets by astronomers when they're trying to imagine, so you discover there are planets around some distant star, and you say, well, is that a place there could be any life? They typically say, is there any planet in the Goldilocks zone? The Goldilocks zone is not too hot, it's not too cold, it's just right. And of course, you'd also ask questions about the size of the planet. Is it too large, is it too small, or is it just right? All right, so my contention is that for Einstein metrics, 4 dimensions is a kind of Goldilocks zone. So what we're going to see in these lectures is that in dimension 4, the existence of Einstein metrics is actually quite subtle. It depends on the differential topology. After all, this is a differential equation for the metric, and you have to be able to differentiate. You can't just say, given a topological manifold, can I try to solve Einstein's equations? You're specifying a smooth structure, a differentiable structure. It turns out that in dimension 4, then the typical situation is you have, unlike in higher dimensions, you typically have infinitely many distinct smooth structures. There are lots of exotic smooth structures on a 4-manifold. And this does not happen in high dimensions. So in high dimensions, there are celebrated theorems like that began with Miller's discovery that the seven-sphere had exotic differential structures. And, but it turns out that it's always, in that setting, you always only get a finite number of differential structures on high-dimensional manifolds, whereas in dimension 4, it's typically you get infinitely many distinct smooth structures, countably many, but infinitely many different smooth structures on a fixed manifold, topological manifold. All right, so we'll see that there are topological four-manifolds which admit an Einstein metric for one smooth structure, but not for many others. Now, I mentioned before how there's a role played in the proof of, for example, the Poincare conjecture, but also more generally, Perlman's program actually led to the resolution of the Thurston's geometrization conjectures, which is given a three-manifold, show that it could be built up from standard pieces, each of which has a good geometry. And so, in dimension 4, most four-manifolds will turn out not to have Einstein metrics, but the kind of theorems we'll be discussing in this course, they don't preclude the possibility that maybe you can break up a four-manifold into pieces which have Einstein metrics, and then by some standard gluing method, you could assemble a more complicated manifold. So keep that idea in mind and be ready to pester me with questions about it if you find it interesting. But the point, so this is pie in the sky. It's not something where we know how to do this. But if you were to naively try to do Ricci flow in dimension 4, one reason for doing that is maybe in the hope that maybe you could break up four manifolds into some geometric pieces. And that's what happens in dimension 3. It's not that every three-manifold admits a metric of constant sectional curvature, but rather that you can break up an arbitrary three-manifold into the pieces which either have either a constant sectional curvature metric or which have a kind of collapsed geometry. All right, so the main point that I'm going to make now is that, so we just saw that in dimension 5, I did not hint very explicitly at how you would go about proving these theorems. I don't need to know that. But in high dimensions, it turns out that a simple manifold like a sphere can have a moduli space of Einstein metrics which has infinitely many different connected components. There are lots of non-standard geometries. When I say that in that dimension 4 for the Einstein problem is there's more rigidity, it turns out that there are circumstances in which you can prove that if you have an Einstein metric on certain four manifolds, it is actually an intelligible metric that you would recognize. So on the other hand, in high dimensions, there's all of this crazy flexibility. The Einstein condition seems to be too weak to learn very much about high-dimensional manifolds. Fortunately, that's also in the context where it turns out differential topology is well understood anyway in high dimensions using completely different techniques. And so it might be cute if you could do something with Einstein metrics on high-dimensional manifolds, but there's no pressing need. Whereas actually, dimension 4 remains a place with very peculiar wild phenomena, which we're still just trying to understand. All right, so in terms of these rigidity phenomena, the first example I would give is a theorem proved by Marcel Berger, our late friend, in the 1960s, where he proved that if you have an Einstein metric on a torus, a four torus, so that's the Cartesian product of four circles, that any such metric is flat. So the typical way that you would construct a flat metric on a 4 torus is you would take R4, choose some basis for R4. That generates a lattice when you take the free abelian group gotten by adding multiples of those basis vectors together. So that gives you a subgroup of R4, which looks like, as a group, it's Z4, but the action can depend on these angles, right? And now you take the quotient, and the flat metric on R4 will descend to the quotient. So, metrics which have 0 sectional curvature, have 0 Ricci curvature, those are Einstein metrics. What is remarkable is that Berger showed that actually those metrics are the only Einstein metrics on the 4 torus. Now, it's important not to confuse this. So if this is the first time you've thought about any of these things, you're not going to jump to the wrong conclusion. But for people who know more, it's important to realize, so I'm saying this does not generalize to higher dimensions. The issue is, so if you were to say, try to classify Ricci flat metrics on the N torus, it goes back to Bachner in the 1940s that you can prove that a Ricci flat metric on an N torus has to be flat. But here, related to your question, we're not specifying the Einstein constant. How do we know that the Einstein constant can't be negative? It can't be positive because positive Ricci curvature would mean finite fundamental curve. How do you know that the N torus does not have an Einstein metric with lambda negative? You can prove this is impossible in dimension 4. We have no idea when N is bigger than 4. Okay, so it's not that there's only one Einstein metric on the 4 torus. There's a moduli space of them because you're choosing an arbitrary basis, and then you'll get an isometric metric only if the two bases are related by a rotation. If you allow for rescaling, there's a 9-dimensional moduli space of flat metrics on the 4 torus. But the important point is it is connected. Okay, so any two flat metrics on the 4 torus are actually joined by a path of flat metrics. The next theorem that was of this flavor, which was proved, was by Nigel Hitchin in the 1970s. And he showed that any Einstein metric on a certain four-manifold, K3, is actually Ricci flat and Taylor. Those kinds of metrics are now called Calabi-Yau metrics, but that Yau had not proved that they existed yet. So which manifold are we talking about? This is a certain simply connected four-manifold, which we will get to know better, called K3, and I will tell you later on why it's called K3. For now, it's enough to say that if you take a homogeneous 4th degree equation in 4 variables, and then that 4 complex variables, that will cut out a hypersurface, a complex hypersurface in CP3. And it turns out that these belong, if you require there are no singular points, the set of such equations is connected, and then it implies that there's only one diffeotype. This is a strange manifold. The first time you see it, I'll explain a little bit more about it in this lecture, but we'll find out more about it later. So, but this interesting simply connected manifold, it turns out Hitchin showed that that if you had an Einstein metric on it, it would have to be Ricci flat and it would have to be Kähler. And building on this idea, one could eventually show that the moduli space of Einstein metrics on this simply connected four-manifold is actually connected. And you can describe, there's a very perfect picture. You can describe exactly what the moduli space looks like, even though none of these metrics can be written down explicitly. You can write down approximations. We don't know the metrics explicitly, but we know the moduli space exactly. So in fact, the moduli space of these metrics is 3 times 19 dimensional. It's 57 dimensional if you allow for rescaling. And it was actually a very huge project of many different people that led to a good theory of showing that the moduli space of these metrics is connected. It's related to work on Kodaira, and also I could mention Alve, that it's about the complex structures on the standard K3, together with later work of Yao on the solution of the Claude conjecture, then work of Kobayashi, then Xiu, and then some work of Kobayashi and Todorov. All right, so these are examples where we know the moduli space exactly. And so in the first case, I said, if you look at a little piece of this manifold, is it the 4 torus? Here's an Einstein metric on it. Well, you would know it's a flat 4 manifold and up to covering. It turns out those are all any such flat compact 4 manifold is a finite up to a finite cover. It's the 4 torus. And there's a similar covering issue here for K3s. But if you look at a little piece of one of these metrics, if you knew that it was Ricci flat and not flat, and it's also what's called a Kähler metric, as I'll explain later on. If you had a little piece of that, and you were told this is a piece, you're looking at a piece of a compact 4 manifold, and it is actually Ricci flat. It's Einstein everywhere. Well, you would know the Einstein constant by looking at little piece, but it'll turn out that up to covers that little. If you also knew the manifold was simply connected, you would already know it's K3. There's a beautiful theorem. So Gilles Courtois is here today. He was one of the triumvirate that proved the following remarkable theorem. So there's if you look at compact quotients of hyperbolic force space, it turns out it's not obvious, but with some work, you can show that actually, if you take hyperbolic force space, that's to say the unique simply connected Einstein manifold, which is also of constant sectional curvature, where the sectional curvature is negative, conventionally you normalize it to be, here this would be -3 for the standard metric, but you can of course multiply it up and down if you want, J. But up to diffeomorphisms and rescalings, it turns out if you take any of these compact quotients of hyperbolic space, modulo a group of isometries, then in fact, so that would be built so that the hyperbolic metric descends to the quotient. And the remarkable theorem is that the only Einstein metrics on such a manifold are the hyperbolic metric, except you have this freedom of, you can rescale it if you want, and you can move it by diffeomorphism. With up to that freedom, there's only one Einstein metric on that manifold. In other words, the moduli space of Einstein metrics on what's called a compact hyperbolic 4 manifold. For such a 4 manifold, the moduli space is actually a single point. When I found out about this theorem, it was about the time that Seiberg-Witten theory came into existence, and within a few months of hearing Gilles Courtois give a talk at Stony Brook about their theorem, I realized that there was an analog one could prove. Part of the proof is analogous, and then there's a different part of the proof that is completely different. And actually, there are still mysteries about how you prove these two theorems using more or less the same machinery. So here, there's a different infinite class of compact complex hyperbolic four-manifolds. So these are things which naturally arise as manifolds with a complex structure. The universal cover as a complex manifold is the unit vol in C2. That has a symmetric space metric. So it has a metric which does not have constant sectional curvature, but which does have the property that the curvature tensor has covariant derivative 0. So these are, that condition is called locally symmetric, and it is a natural generalization, first really systematically studied by Eddy Calton, of the condition of constant sectional curvature. So I remember as a student being confused, constant curvature. Does constant curvature, people usually say constant curvature when they mean constant sectional curvature. Locally symmetric spaces also have, in a certain sense, have constant curvature. That's to say that their curvature tensor is covariantly constant. Covariant derivative of the curvature tensor is 0, but that is a weaker condition than demanding that the sectional curvature is constant. All right, so in both of these cases, it turns out that the moduli space is a single point. One thing that's playing a role in both of these cases is the phenomenon of Mostoff rigidity. When you look at a hyperbolic 2 manifold, if you take hyperbolic 2 space, and you look at a quotient of that by a group of isometries, then it turns out that you get, by that construction, any compact Riemann surface of genus greater than or equal to 2 with an arbitrary conformal structure. And then the uniformization theorem ends up saying that if you take a genus 2 surface or a genus 3 surface, higher genus surface, those all admit metrics of constant sectional curvature. So metrics of constant sectional curvature have a kind of classical familiarity. Of course, for surfaces, that's constant Gauss curvature. But there is a big difference between dimension 2 and dimension 3 for this subject. Constant sectional curvature for a compact manifold in dimension 2 with negative sectional curvature. It turns out there's flexibility. There's a moduli space, non-trivial moduli space of, let's say on a genus 2 surface, there is a non-trivial moduli space which has real dimension 6. But it turns out the surprising thing is that if you instead have a hyperbolic 3 manifold, hyperbolic 4 manifold, those are actually rigid. Not just infinitesimally. It's not that you can't perturb the metric among constant sectional curvature metrics. There's a very powerful theorem which says that if you have a constant sectional curvature metric with that fundamental, on a manifold with that fundamental group, there's only one of them. And so when that was first discovered, I think it was first discovered by Mostow in dimension 3, it was considered a shock. Eventually it turned out to be part of a much larger rigidity. And so the work that Besson, Courtois, and Gallo had done, in particular, illuminates this difference between dimension 2 and higher dimensions in a very interesting way, because in particular, their work also gives a new proof in the hyperbolic setting of Mostow rigidity theory. All right, so here are various cases in dimension 4 where we have compact manifolds. And there are a few others. There are a few others related to these that are not literally on the list here. But yes.
In the three-dimensional case, in the geometrization conjecture, there were 8 types of pieces.
Yes.
Should I think of those as 4 types of pieces with parameters?
No. So it's a very interesting question. When you're trying, the right question would in general be, how do you generalize the geometrization of 3 manifolds to something high dimensional? And there is a naive, there are people that have tried naive programs of trying to say, well, what are the pieces, the standard pieces? from my own point of view, this is the wrong way to think about the geometry of four-manifolds, because if you won't, so the theory of four-manifolds is very, very rich in terms of possible differentiable structures, and if you try to reduce it to just gluing together standard pieces, you're never going to get close to the richness of what's actually out there. There are, what this is illustrating is that there are certain four-manifolds where the Einstein condition is already enough to reduce the geometric structure to a connected family of geometries. So in this case, the K3 case, or in the torus case, we don't get a unique geometry, we get a family of geometries. Yes?
So if you take the topological K3 surface, we have at least countable in any smooth structure.
Yes, and what we'll see, this is a very interesting question, it's getting ahead of us a little bit, but I'm glad you asked it. So it'll turn out that there are countably many different differentiable structures on K3. And here, when I say K3, I'm referring to a specific differentiable structure. The argument that proves Hitchin's theorem also shows that if you were to have an exotic K3, if you had K3 with a different differentiable structure, it could not admit an Einstein metric. So there's a standard smooth structure on K3, and that is uniquely picked out by the condition that it has an Einstein metric. Yeah, thank you. So it's these are already some rich examples, but I'm not going to be able to show you a lot more a large family of new examples where we get a kind of unique Einstein geometry for let's say the topological structure. But in that same spirit as that question, so the theorem of Besson-Courtois-Gadeau shows that if you have another manifold that is homotopic equivalent to a compact quotient of hyperbolic space, then if it admits an Einstein metric, it actually is this manifold with its standard differentiable structure. If it was instead something exotic, it would not admit an Einstein metric. And so here, it turned out if you have something which is topologically K3 but not differentially K3, it will not have an Einstein metric. There's only one smooth structure for which there's an Einstein metric. Okay, so there's something really weird going on in dimension 4. What is it? Well, there is a peculiarity in Lie group theory that one might notice, but just think, well, who cares? The rotation group in dimension 4 is SO4. Now, SO4 has the following property. It is not a simple Lie group. So its Lie algebra is not simple. The higher dimensional rotation groups, let's say SO5, SO6, and so forth, those are all simple Lie groups. They have simple Lie algebras, and that means that if you take there's no Lie subalgebra which is invariant by under Lie bracket. SO4, on the other hand, has this peculiar property. SO4 up to passing to its double cover, which is sometimes called spin 4. Its double cover, its universal cover, is actually a product of two Lie groups. So here, the Lie group in question, you have two copies of SP1, and in my notations, SP1 is a compact group, which is actually just the three-sphere. How do you give the three-sphere a Lie group structure? You can think of it as a subgroup of the unit quaternions. So you think of it as a subgroup of the quaternions. It's the set of quaternions of length 1. Okay, so under quaternionic multiplication, quaternions look like R4 with a certain multiplication. The non-zero quaternions actually form a multiplicative group. It's a Lie group. It's not compact, but it has a compact subgroup. But the three-sphere, the unit three-sphere, is actually a subgroup of the multiplicative quaternions. And there is a nice action of SP1 times SP1, with pairs of unit quaternions, acting on R4, thought of as the quaternions H. And it's that what you can do is multiply on one side by the first quaternion, and multiply on the other side by the inverse of the other quaternion. And so this defines a homomorphism from SP1 times SP1 to S4. What's not so clear here is that this preserves length. This action is actually, it preserves the standard length. And the reason is that if you take two quaternions and you multiply them, and then take the norm, then what you get is that the length is multiplicative. In other words, this is a nice generalization. You're used to the fact that when you multiply complex numbers, their norms multiply. And the same thing is true of quaternions. So this has the consequence, if Q1 and Q2 are unit quaternions, then this new element of the quaternions has the same length as the original one. That's a linear map, real linear map that preserves length, so it must be an orthogonal transformation. This is also a connected group, so the image of SP1 times SP1 is a connected subgroup of the, not just of the orthogonal group, but rather of its identity component, which is SO4. And the cute point is that, well, SO4 has dimension 6. This is a 6-dimensional Lie group. You can check on the level of things that are very closely identity. The corresponding morphism of Lie groups is injective, so this must be a covering map. And so immediately you find from the fact that this is compact that it's actually surjective. And the kernel of this, if you multiply on one side by -1, and you multiply by the inverse of -1 on the other side, that's the identity map. So this does have non-trivial kernel, exactly the kernel of this map from SP1 times SP1 to SO4 is Z mod 2. By the way, a nice thing happens if you restrict this to the diagonal. So if you take Q1 and Q2 to be equal, so this is then this action is conjugation by Q1. Conjugation by Q1 fixes the identity element in the quaternions, but since these are orthogonal transformations, it has to therefore act on the orthogonal complement, the imaginary quaternions, which is a copy of R3. So there's a nice map from SP1 to SO3, built in the same way, just by taking Q1 equals Q2. And again, the kernel there is plus or minus 1. And so one way of describing SP1 is it's the double cover of SO3. So SP1 times SP1 is often described as spin 4. It's the universal cover of SO4. SP1 is spin 3. It's the universal cover of SO3. All right, so when you look at this on the level of Lie algebras, what you conclude is that actually SO4 has to be a sum of two other Lie algebras, and each of those Lie subalgebras has to be isomorphic to SO3. Now, This is a statement, though. What is the Lie algebra of SO4? I mean, it's the skew 4x4 matrices. This is saying that if you have a skew 4x4 matrix, you can represent it in terms of two skew 3x3 matrices. In particular, there are these kind of preferred subspaces of the space of skew 4x4 matrices, and that is invariant under the adjoint action of SO4 on its Lie algebra. So the rotation group acting on this Lie algebra of skew 4x4 matrices actually leaves two three-dimensional subspaces invariant percent of themselves. But how else do we like to use skew matrices in differential geometry? If you look at a two-form in an orthonormal frame, its components form a skew matrix. And how does the rotation group act on it? It's exactly by the adjoint action. So if you're thinking on the level of representations of SO4, this Lie algebra SO4 can also be thought of as the set of two forms on R4. The set of two forms on R4 has an invariant decomposition into two three-dimensional subspaces that's invariant under the action of SO4. Well, in fact, there is a deeper meaning here. If you have an oriented Riemannian four-manifold, then its bundle of two forms naturally splits into two three-dimensional subbundles. And fiber by fiber, what's going on in terms of representations of SO4, it's the same decomposition of this six-dimensional space into two three-dimensional subspaces. There is a natural decomposition of the bundle of two forms on an oriented Riemannian four-manifold into two rank 3 vector bundles. And these, so rather than constantly referring to the representation theory of SO4, these have a very simple concrete meaning. Namely, these two subspaces are the eigenspaces of the Hodge-Star operator. The Hodge-Star operator, the basic idea in this context would be that what does a two-form really mean? If you have a Riemannian metric, then if you have and you take an oriented two-dimensional subspace of the tangent space, a two-form is something that assigns a number to each two-dimensional subspace. Right? The way it varies as you vary, it's a little bit complicated. As a function on the Grassmannian of two planes, it's a slightly, you can actually characterize these functions, but the main thing is to remember, a two-form is something that assigns, in the presence of a Riemannian metric, a two-form assigns a number to every oriented two-plane. But in dimension 4, given a two-plane with an orientation, there is a uniquely associated orthogonal two-plane, which then is endowed with a natural orientation given an orientation on the ambient space. But what is that actually, this operation then? If you say, well, there's a map from two planes to two planes, from oriented two planes to oriented two planes, that gives some map actually from a map from the two forms to the two forms. That's called the Hodge-Star operator. So the Hodge-Star operator is an operation in this dimension. So because 2 is the middle dimension, the Hodge-Star, so in general, Hodge-Star would send a P form to an n minus P form. If P is 2 and n is 4, then it sends two forms to two forms. And it happens that, so it's always the case that when you square the Hodge-Star operator, you get either +1 or -1, and there's an algorithm for deciding what the sign is. In dimension 4, the Riemannian metric, you'll find that the star squared is 1. So the possible eigenvalues are plus and minus 1. So the +1 eigenspace is called self-dual two forms. I'll make this more explicit in a moment. There's a subspace of self-dual two forms, and there's a subspace of anti-self-dual two forms. Now, before we go further, why is this something important? I mentioned before something about the how to think about the curvature tensor of a Riemannian metric, and that's to say that curvature is a two-form with bundle values. And it's a universal feature of the geometry of connections on fiber bundles, that if you have, for example, curvature on a vector bundle, curvature of a connection on a vector bundle, the curvature will always be a two-form with values in a bundle. For example, it might be the endomorphism bundle of a certain vector bundle. So if you have a vector bundle E with connection nabla over an oriented Riemannian four-manifold, so here E could be of arbitrary rank, take any connection, then the splitting, you can split up two forms into self-dual and anti-self-dual pieces, and this then shows up by saying that the curvature of the vector bundle has a self-dual piece and an anti-self-dual piece. So F plus or minus would be something in the self-dual or the anti-self-dual, two forms with values in endomorphism bundle. In the special case, when the anti-self-dual part of the curvature vanishes, so that the curvature is in fact a self-dual two-form F plus, then we say that the connection is a self-dual connection. And the study of these self-dual connections, turns out these connections that satisfy this also satisfy, these are special solutions of the Yang-Mills equations. What Donaldson did, starting in the early 1980s, was to study moduli spaces of self-dual connections. So here you look at connections modulo the gauge group of endomorphisms of the bundle. And what he showed is that it was possible under certain circumstances. Typically, most of the time he was looking at bundles of complex bundles of complex rank 2, equipped with a unitary structure. He studied in that context self-dual connections, and for appropriate values of the first Pontryagin number, he was able to show that one could extract differential topological invariance of the four-manifold. These are still very, very interesting invariants. So-called there are things called Donaldson polynomials, for example, that are extracted from this theory. This was the first theorems that showed that some topological four-manifolds had more than one differentiable structure were found by means of considering these so-called self-dual connections and using the space, extracting topological invariance by studying the moduli spaces of self-dual connections. Now, I'm not going to talk about those invariants called Donaldson invariants in my lectures, but I will tell you about Seiberg-Witten theory, which is a related system of equations which are simpler and which in practice seem to contain more or less the same information. But the main difference is that unlike Donaldson invariants, so Donaldson invariants do not have any obvious direct relationship with Riemannian geometry. It turns out the Seiberg-Witten equations actually give rise to surprising theorems in Riemannian geometry. All right, so far, I told you that the Lie group SO4 is not simple, and that leads to a decomposition of two forms on an oriented Riemannian manifold into self-dual and anti-self-dual pieces. The way I described it, if this is the first time you've seen this notion of self-duality, anti-self-duality, it probably seems like I'm speaking Greek, and maybe Greek is your native language, but if it's not, you need an explanation, right? So here are some examples of self-dual two forms. In an oriented orthonormal basis, then E1 wedge E2 has Hodge star equal to E3 plus, wedge E4, and if you take the sum of those two things, the resulting form has the property that it's its own Hodge star. Another example would be E1 wedge E3 has Hodge star minus E2 wedge E4, and if you're curious about what is the sign, the point is that if you wedge this with that, you get the volume form E1 wedge E2 wedge E3 wedge E4. So here, it's a minus sign because when you wedge this with that, and you want to get E1 wedge E2 wedge E3, there has to be a minus sign here. Okay? So here I've written down 3 examples of self-dual 2 forms relative to an orthonormal frame. These all have the same norm. Standard conventions, these are actually not a unit norm, they have a norm square root of 2, but who cares? These are actually these are actually giving a basis for the self-dual 2 forms. These are all orthogonal to each other with respect to the standard product. So the point is that as you apply an element of SO4, it would turn out that there's an induced action on R3, taking these to be the basis. So every 4-dimensional rotation gives rise to a 3-dimensional rotation on the self-dual 2 forms. But we could also say that the same thing for the anti-self-dual 2 forms, and all of these is a change appropriate signs. So one of the charming things about 4-dimensional geometry, you say it's hard to see 4 dimensions, but actually you're trying to understand a rotation in 4 dimensions. Well, it's essentially just 2 rotations in 3 dimensions. One R3, one view screen is an R3, which is actually the self-dual 2 forms. The other view screen you want to be thinking about is the anti-self-dual forms, and an arbitrary 4-dimensional rotation up to sine is represented by two rotations in 3 dimensions. In other words, if you take SO4 and you mod out by a subgroup consisting of plus or minus the identity, then that's isomorphic to SO3. Okay, so but I've already emphasized curvature is always a 2 form with bundled values. In the Riemannian case, though, you could say, what bundle does it take values in? Well, it's the skew endomorphisms of the tangent bundle. That's in a different way of saying it's basically a 2 form with values in 2 forms. Okay? So the more abstract, you could say that, given 2 vectors on a Riemannian manifold, you can feed them into the curvature tensor, and what you get is an infinitesimal rotation in dimension n, where your manifold is an n-manifold. Infinitesimal rotations in dimension 4, well, actually, in dimension n, that's a 2 form with values in 2 forms, any dimension, for the Riemannian connection, and that really just has to do with the fact that it's metric sympatical. So here, if we're looking at the structure of the curvature tensor in dimension 4, we can think, well, the curvature can be thought of as a linear map from 2 forms to 2 forms. But we know how to split up two forms into 2 pieces, the self-dual and the anti-self-dual 2 forms. And we now, therefore, get a decomposition of the curvature tensor into 4 pieces. Now, if this is not an arbitrary linear map. It turns out that Bianchi identities tell you that it's actually self-adjoint. Writing out in an orthonormal basis, it would be represented by a symmetric matrix. So if we think of the 2 forms as being the self-dual 2 forms plus the anti-self-dual 2 forms, then you could say, well, the curvature tensor can be thought of as a linear map from, it has pieces, one of which is a linear map from lambda plus to lambda plus. It also has a piece which is a linear map from lambda minus to lambda plus, and so forth. One charming point how many components do we have here? 9, 3 times 3. How many components does the Ricci tensor have in dimension 4? Well, it has 10 components because it's represented locally by a symmetric 4x4 matrix. The trace tree piece of that has 9 components. Turns out that this off-diagonal piece here it faithfully encodes the trace-free Ricci tensor. And the fact that this is actually self-adjoint ends up saying, well, these two blocks, the part that's in lambda minus tensor lambda plus, or homomorphism from lambda minus to lambda plus, it really is just the adjoint of this other thing, which is a linear map from lambda plus to lambda minus. Both of these are encode exactly the same information. They really are just modified forms of the trace-free Ricci tensor. Whereas, what do we see on the diagonal? Well, the scalar curvature shows up as a multiple of the identity. So it's actually, that contribution is the same in both of these blocks. The fact that this block has the same trace as that block is an interesting consequence of the Bianchi identities, because the Bianchi identities would say that if you have the curvature tensor and you contract it with the volume form, which also has 4 indices, you must get 0. It's related to the fact that so I mentioned before, the place where the curvature tensor lives is that it's a symmetric form on, it's in the symmetric product of lambda 2 with itself, but it has the property that it's also orthogonal to the 4 forms. So there's one such Bianchi identity here, which is saying that the trace here is equal to the trace there. And then, well, there's some other piece. There's the trace-free piece of this block and the trace-free piece of that block. So these other two pieces are called the self-dual Weil curvature and the anti-self-dual Weil curvature. And if you've never heard of the Weil curvature before, this would seem very mysterious. But Hermann Weil was the first person to study what piece of the curvature tensor is algebraically independent from the Ricci tensor. There is a piece of the curvature which has nothing to do with the Ricci curvature that you read off from a trace. And that is called the Weil curvature, but what Hermann Weil discovered is that that part of the Weil curvature is actually linearly, it's not just that it's linearly independent. The Ricci curvature changes in a complicated way if you multiply the metric by a function, but this Weil piece is unchanged by multiplying the metric by a constant. Strictly speaking, when I say that it's that it is, so the natural way that you would write if you decompose the curvature tensor into this Weil piece plus a Ricci piece, so this Ricci piece involves, so I won't write, it's easier if you raise one index. All right, so the Hermann Weil's curvature tensor, like the ordinary curvature tensor, is something which you feed it 3 vectors and it pops out a vector. So this is something that eats 3 vectors and a 1 form. But in this decomposition, one is really raising an index. So here you use the metric to raise an index, and then I can more easily say that this is a constant here times the Ricci tensor and then there's another constant depending on the dimension times the scalar curvature. Okay, so well, these are constants that depend upon the dimension. That's the way the decomposition goes, and it's just an algebraic decomposition of the curvature tensor. So what really pops out here is to say that, so here W is actually a sum of 2 pieces. In In higher dimensions, you don't get anything further, but in dimension 4, it turns out that there is also an invariant decomposition of the Weil tensor into self-dual and anti-self-dual pieces. All right, so the things that appear there as W plus and minus are actually pieces of this gadget, and they would have the property that naively, if you multiply the metric by u squared, it would actually multiply these by u to the minus 2. But if you then say, oh, well, those correspond to things which are in the tensor product of 3 copies of the cotangent bundle, a tensor 1 copy of the tangent bundle, then that has conformal weight 0. It's literally unchanged if you multiply the metric by a constant. And by the way, so if that all seems kind of impenetrable, the first consequence of Weil's discovery there is that, for example, in dimension 4, if you have a metric which has non-trivial Weil curvature, then you cannot find coordinates in which it looks like Euclidean metric times a function. Because Euclidean metric times a function would have vanishing Weil curvature. This piece is not changed by multiplying by a constant. And so in the same way, starting in dimension 4 and above, that gives a proof of the fact that most metrics are not locally conformally flat. There is also an obstruction in dimension 3, which is more subtle. And in fact, there's an early book by Schouten which claimed that in dimension 3, all metrics are conformally flat. That's not true. There's another obstruction which actually was discovered before Weil by Couteau. Didn't get very much attention at that time. It was a very interesting higher order obstruction. All right, so that's the decomposition of the curvature tensor in dimension 4. What is the Einstein condition? It's that the trace-free Ricci tensor vanishes, right? If you're on an Einstein manifold, it would exactly be saying that there's no off-diagonal block, just 0. So being Einstein would just say the Hodge star actually would be the map which acts on the self-dual forms as +1, acts on the anti-self-dual forms as -1. The Hodge star in this picture really looks like the matrix. That's the Hodge star as a map from 2 forms to 2 forms in this picture, right? So having no off-diagonal piece is exactly the same as saying that it commutes with the Hodge star. So what does this mean in sort of simple terms without using any formalism? The Hodge star has to do with replacing a two-dimensional subspace of the tangent space with its orthogonal complement, saying that this operation has no influence on the curvature tensor is exactly saying that if you take the sectional curvature, if you have a Riemannian four-manifold, take a two-dimensional subspace of the tangent space, observe that it has a two-dimensional orthogonal complement. If you tilt your head, that's obvious, right? So, take picture, of course, but I'll trick you. So given a two-dimensional subspace of our four-dimensional tangent space, it has an orthogonal complement, and we can ask, so P, the plane, two-plane P, it has a sectional curvature. P plus also is associated with the sectional curvature. The Einstein condition is exactly saying that you're on a four-manifold where for every two-plane, its sectional curvature is exactly the same as the sectional curvature of the perpendicular two-plane. And if you feel like you've been bamboozled, a nice challenge is that you can prove this without using any of the formalism that I've introduced for this subject. Without discussing the Hodge star and so forth, you can actually prove this directly. But it looks like a completely mysterious fact. if you don't introduce this way of thinking. All right, so for a compact Riemannian four-manifold, I introduced pieces of the curvature tensor in any even dimension. If you're in dimension 2m, there is a homogeneous polynomial in the curvature tensor, which is invariant under the action of the orthogonal group, having the property that its integral is a multiple of the Euler characteristic of the manifold. So this is what I've written down here. I made it explicit. In dimension 4, there is a certain quadratic expression in the curvature tensor, which is invariant under the orthogonal group, such that if you take its integral, you get the Euler characteristic. And in fact, this expression, this integrand, is usually called the Pfaffian of the curvature. It really has to do with the fact that if you think of the curvature as being in lambda 2 tensor at lambda 2, what you can do is if you tensor two copies of the curvature tensor, then you can extract from that something that's in maps from the four forms to the four forms. But the main point is that because it's invariant under the action of the orthogonal group, a little bit of representation theory would easily say that these, so we have here the scalar curvature squared, the self-dual Weyl curvature squared, the anti-self-dual Weyl curvature squared, the trace-free Ricci curvature squared. Those are invariant quadratic expressions in the curvature tensor, and what you can show is that they're the only invariant quadratic expressions. Any quadratic expression in curvature which is invariant under the orthogonal group is a linear combination of those four expressions. So if you know the statement of the Gauss-Bonnet theorem in dimension 4, the only puzzle would be what are the coefficients of these pieces. And if you didn't know the more general thing, that what you're really trying to do is simplify the Pfaffian and put it in a recognizable form, you could just look at 4 well-chosen examples and read off what these coefficients have to be. It's a good way to check. So this is the four-dimensional case of the more general generalized Gauss-Bonnet theorem. Of course, it generalizes the fact that the integral of the Gauss curvature on a surface is a multiple of the Euler characteristic. But in dimension 4, it takes this beautifully concrete form. Now, for the theory of Einstein metrics, the thing to notice is that the only negative coefficient here comes in front of the trace-free Ricci curvature term. If it's Einstein, this integrand would have to be pointwise non-negative. And that actually is the basis of Berger's theorem that an Einstein metric on the four torus, which has Euler characteristic 0, has to be flat. There's one other important invariant of topological invariant of a manifold. These are both homotopy invariants that can be read off from the curvature. So there's one other curvature quantity which calculates a topological invariant. This is related to a theorem. It's really due to dimension 4 to Lemmy-Thom and then generalized to higher dimensions by Fritz Hirzebruch, which is that the signature of a manifold whose dimension is divisible by 4 is expressible in terms of Pontryagin numbers, and Pontryagin numbers are expressible in terms of curvature integrals. So you can actually then extract from that, although they did not actually put it in this concrete form, there is a way of expressing the signature of the four-manifold in terms of actually just an integral involving the self-dual and anti-self-dual Weyl curvatures. What is this signature? Well, it's the difference between the invariant so-called B plus and B minus. You can find this in terms of the intersection pairing on the second cohomology of the four-manifold. If we do it in terms of de Rham cohomology, then there is a pairing given two de Rham classes of closed two forms. What you can do is you can wedge the two forms together and integrate, and then it's a consequence of Stokes' theorem that the answer only depends on the original de Rham classes. If you change phi or psi by adding on an exact form, it doesn't change the integral. But the acute point is that this intersection pairing by Poincare duality is actually a non-degenerate pairing. That's to say, it can actually, you can diagonalize it by choosing an appropriate basis on your cohomology. It can just be thought of as represented by a matrix whose size is the second Betty number. It's positive in a certain number of directions, negative in a certain number of directions. It's a standard, I think it's misleading to say that these are the eigenvalues, because this is really, this is a quadratic form, and the equivalence relation is similarity, it's not, but anyway, you can choose a basis in which it's put in this very simple form. That actually has a very concrete meaning. If we're on a smooth, compact, oriented four-manifold, Hodge theory in general would say that any de Rham class is uniquely represented by harmonic form, and here harmonic can be interpreted as saying it's a closed form whose Hodge star is also closed. And you might notice that Hodge star actually has the property that if you take a class with these properties, you take its Hodge star, well, the Hodge star is also closed, and Hodge star squared is applied to the form as the original thing. So that sends harmonic forms to harmonic forms, and therefore you can, that has square 1, so you can decompose the second cohomology into, as a sum of the de Rham classes of self-dual harmonic forms and anti-self-dual harmonic forms. So initially, these eigenspaces of Hodge star acting on the de Rham classes, you might think that, well, that would satisfy some non-local condition, but it actually turns out to be exactly, there are de Rham classes that are represented by closed self-dual forms, and then there are de Rham classes that are represented by closed anti-self-dual two forms. The sum of those two subspaces is exactly the second cohomology. The warning, though, is this decomposition does depend on the metric. It's conformally invariant. If you multiply the metric by a function, it doesn't change this because it doesn't affect the Hodge star operator on two forms. But in general, the main warning, which we have to eventually deal with, is that as you vary the metric, these subspaces move. All right, so I already pointed out that there's some kind of strong condition that you could deduce if the manifold was Einstein. Let's look at the following. Right now, it looks like a random thing to do, but look at the invariant twice the Euler characteristic plus 3 times the signature of our manifold. And if you apply those former, this combination is chosen exactly so that the anti-self-dual vowel curvature has been canceled out. And so there are only 3 parts of the curvature that appear in this Gauss-Bonnet type formula. The trace-free Ricci curvature has a negative coefficient. The other pieces have positive coefficients. And so what you would find is that if the metric is Einstein, so, I mean, the first line, this is true for any metric, just like the two-dimensional Gauss-Bonnet theorem. It doesn't matter which metric you use, you always, the integral of the Gauss curvature gives you a multiple Euler characteristic. Similarly, the first, in dimension 4, take any metric on your oriented compact four-manifold, when you integrate this combination of curvatures, you'll get twice the Euler characteristic plus 3 times the signature. But if the metric happens to be Einstein, what happens? Well, the integrand is pointwise non-negative, and in particular, the integral has to be greater than or equal to 0. All right, so the Hitch-Thorpe inequality begins by saying if you have a compact-oriented four-manifold that admits an Einstein metric, then twice its Euler characteristic plus 3 times its signature must be non-negative. Now, there's something fascinating that goes on that's more subtle. You could say, what happens in the boundary case? When we look at this decomposition of the curvature tensor, it turns out that that actually when you look at this decomposition of the curvature, it turns out that the first column corresponds to the curvature of lambda plus, and the second it really corresponds to the curvature of lambda minus. And so if we know just that W plus and S and R0 are 0, then we would have a connection for which lambda plus was actually flat. So the first version of this Hitch-Thorpe inequality is that if you have an Einstein metric on a manifold with 2 chi plus 3 tau equal to 0, if you have an Einstein metric on such a thing, then the bundle lambda plus has to be flat. Well, eventually, we'll find out that these metrics with that property are rather rare. They're called locally hyperkähler metrics, and we'll find out more about them later. But let's just see some simple consequences right now. If you have 2 smooth, compact, simply connected four-manifolds, the theorem that Friedman won the Fields Medal for, and that Donaldson implicitly improved by work in the same time frame. So they shared the Fields Medal in 1986. And if you put their results together and massage them a little bit, you actually get the following remarkable statement. Suppose you have 2 compact, simply connected four-manifolds. They're both oriented, and you want to know if they're orientedly homeomorphic. And so this is not a diffeomorphism classification I'm about to tell you. It's homeomorphism classification. And the answer is the conditions. They're obviously necessary conditions, but they are actually necessary and sufficient. The first is they have the same Euler characteristic. The second is they have the same signature. And then there's one other condition. Either both of them are spin, or they're both non-spin. So after you've listened to some more lectures, you'll know how to look at a four-manifold and tell if it's spin or not. But for right now, just to say spin means the second Stiefel-Whitney class vanishes. The second one is that this second Stiefel-Whitney class of the manifold is non-zero. You might think of those as diffeomorphism invariants. It turns out they're homeomorphism invariants. They're actually homotopy invariants because they can be read off from properties of the intersection form over Z2. So the main warning right now is that, so I'm telling you about how to classify, or at least to determine when 2 four-manifolds are homeomorphic or not, orientedly homeomorphic. This is a list of things. These are obviously necessary conditions, but the remarkable thing is that it turns out that these are also sufficient conditions to conclude that the manifolds are homeomorphic. So the warning is this is not a diffeomorphism conjecture, classification, but rather it only tells you when 2 things are topologically the same. So when they are homeomorphic. So it'll turn out that no diffeomorphism classification is currently known. We have a lot of invariants that can distinguish different differentiable structures, but we don't know in any case how to a priori give a classification of the differentiable structures. You can tell that certain things that are homeomorphic are not diffeomorphic. Usually if you want to show that they're really diffeomorphic, it's because you've built them in some very concrete way, and you just go through all the steps of the construction. So what happens is that typically one homeotype actually corresponds to infinitely many diffeotypes. So a nice corollary of this, let's just put it in practice. Suppose we want to classify up to homeomorphism. Oh, and by the way, I should have emphasized one thing about this theorem. I'm assuming that the two given manifolds are smooth, or admit smooth structures. Okay? So here, you might it seems really weird, and Friedman and Quinn and so forth at first were really kind of, they just didn't think it could be the right theorem. That here you get to get a nice this very nice classification, you have to assume that the manifolds are things that admit smooth structures. Otherwise, there are extra invariants, because you see them in the invariants, that you have to include in order to get a classification. If the two things are smooth, the only things that you have to check, they're both simply connected. Homeomorphism, just it's enough to check they have the same Euler characteristic, the same signature, and they're both spin or they're both non-spin. So here's a corollary. Suppose you have two smooth, compact, simply connected, non-spin four manifolds. So suppose you want to classify up to homeomorphism. Compact, simply connected, smooth, non-spin four manifolds. Then up to homeomorphism, here's the complete list. What you can do is you can take iterated connected sums of CP2s and CP2 bars. So here, CP2 is not being thought of as a complex manifold. It's the underlying oriented four manifold. When CP2 has a complex structure, that complex structure determines an orientation. And we're just thinking of it as a smooth oriented four manifold here. Okay? But it has another possible orientation. We put a bar over it, it means the other orientation. This is a standard thing in differential topology. Unfortunately, you might think that's complex conjugation. It's not. Complex conjugation in CP2 actually preserves orientation. Overbar means reverse orientation. All right, so then what is this hash symbol? It's called connected sum. You're familiar with it by building up the surface of genus 2 from two tori. You can do the same thing. You start with two oriented compact manifolds of the same dimension. You throw a standard ball out of each, and then you glue them together on their boundary spheres in a way that, so that there's the orientations, you can orient the connected sum in such a way that the orientation induces the given orientations on the two pieces, okay? That's connected sum. And this, you can do this for oriented manifolds in any dimension. It's a way of building up new oriented manifolds out of given oriented manifolds. And it's called connected sum because it produces a new manifold which is also connected. Okay, so what you can iterate this, right? So what you can take a disjoint union of J copies of CP2 and K copies of CP2 bar, and then you can cut balls out of them and iteratively glue them together by this process. So this may not seem, the way I described B plus and B minus, you thought it had to do with maybe what's the dimension of the space of harmonic forms. You don't have to go find the harmonic forms in order to find out what B plus and B minus is. There's a geometric way of figuring out what the intersection form is on the integer homology, and from that it turns out that B plus will be exactly the number of CP2s, and B minus will be the number of CP2 bars. And I'll say in the next lecture a little bit more about why that's true. So so if you're looking for lots of examples, you may not have thinking of compact four manifolds. Well, maybe you didn't know very many before. Here are a lot of them, and actually this is a topological list. If you're only interested in exhausting the possible homeotypes of smooth manifolds, among the simply connected non-spin ones, these are the only things that you can construct. Anything will be of this topological type, although the warning is there are usually infinitely many different differential structures on each of these. What if we look at the Hitchin-Thorpe inequality for these non-spin manifolds? So if we take the connected sum of J CP2s and K CP2 bars, the Euler characteristic will be, so the second Benny number is J plus K, so and B1 and B3 are 0. So this will end up having Euler characteristic 2 plus J plus K. The signature is B plus minus B minus, so it's J minus K. And if you now look at 2 chi plus 3 tau, that will be 4 plus 5J minus K. And so now notice that you get a non-trivial condition here for this to have an Einstein metric. And that would be an obstruction no matter which, it doesn't depend on which the differentiable structure you have, right? Because this Hitchin-Thorpe inequality really is saying something about the homotopy. So what you find is that for if K is positive, then J also, if K is positive and it's not too small, you're going to have a realm of J. And also, if J is given, well, K can't be too large. Now, these are non-spin manifolds, and it turns out that the bundle lambda plus has the property that its second Stiefel-Whitney class is the same as the second Stiefel-Whitney class of the Four-Manifold. So actually on all of these manifolds, lambda plus is a non-trivial bundle. Okay? Lambda plus, the bundle lambda plus of the sub-bundle of the two forms. Turns out to be non-trivial on all of these four manifolds because they're non-spin. So these are simply connected manifolds. If there was a connection on lambda plus that was flat, by parallel transport, that would give a trivialization of lambda plus. So for all of these manifolds, actually, lambda plus can't be flat, and therefore, a little further analysis of Hitchin-Thorpe said that even the equality case can occur if you have an Einstein metric. 4 plus phi j has to be strictly bigger than k. And the last observation is, well, the Einstein condition doesn't have anything to do with the orientation. But B plus and B minus do depend on the orientation. If you switch the orientation, that's essentially interchanging J and K. So in fact, you get a second inequality that would have to be true. 4 plus 5K would have to be less than J. And so now, when you think about this a little bit, you'll be able to find huge numbers of compact, simply connected four manifolds that can't admit Einstein metrics. The simplest example would be, suppose you took a connected sum of 4 copies of CP2 and no CP2 bars. All right, so then you would be in this case when if you only had CP2s, no CP2 bars, K would be 0, J would be whatever you like, right? So if J is 4 or larger, you can't have an Einstein metric. Or another example, suppose you were to take a connected sum of CP2 with K CP2 bars, right? You would then find, so J is 1, and then you would find that actually if J is 1, well, K has to be smaller than 9. And you'll see that inequality at play in later examples, okay? So there are homotopy obstructions to the existence of an Einstein metric coming out of these Gauss-Bonnet type formulas. Now, this is just the simplest example. There are lots of simply connected four manifolds that do not admit Einstein metrics, but these are not the only obstructions. We'll later find out that there are more obstructions which depend upon which differentiable structure you have on your manifold. And that will be one of the subjects I'll try to explain in the coming lectures. Well, that's plenty for today. I hope I'm surprised your eyes are not all glazed over. Some of you are still awake. 3 hours is a long time. But I hope that these will be useful and interesting lectures. And please feel free to talk to me right now, or email me. You can easily get my email address and email me. If you would like more details about certain things I said today to be re-explained in another lecture, if you feel I'm going too fast or if I'm going too slow, please tell me. I hope I'm trying to hit the happy medium where the experts won't be too bored, and on the other hand, where the lectures will be comprehensible to people who are just learning about the subject. But I'm definitely very happy to change the pace of the course depending upon comments I get from you in the next week. So that's enough for today. Thank you, and I'll see you next week. Any questions people want to ask publicly? If not, you can come down. Yes.
So, for this curve area, in the non-speed case, do you really need balance or it's just Friedman specification?
Yeah, so, well, the thing that's not obvious, so you do need Donaldson even in the non-spin case. If you're looking at topological then there are some with positive intersection form, which are simply connected and actually non-spin. So most of it turns out that when you're looking at the classification of definite quadratic forms over the integers, it's extremely complicated. And actually, Friedman claimed that Quinn exclaimed when Donaldson came out with his theorem, this isn't fair. I mean, there are so many intersection forms which would be candidates otherwise. They exist as topological four-manifolds. They can't have a smooth structure. So, so there are, if you were looking at the things that are excluded by this theorem, the first things you would think of would be maybe direct sums of E8s, and those correspond to 8 manifolds, to spin manifolds. And so, for example, there is a simply connected spin four-manifold with intersection, which is topological but not smooth, which has intersection form E8. But when you look at forms of large rank, there are odd ones also, which are positive definite. They're sort of not as celebrated, but yeah, they exist. And anyway, those are all excluded. So it turns out that somehow the classification of topological four-manifolds is extremely complicated, even in the simply connected case, exactly because
even in the definite case.
Even in the definite, so if the intersection form is definite, it's actually quite complicated. In the indefinite case, non-spin, it just comes down to these connected sums. But the thing that Donaldson's theorem comes to play on is, in the definite case, it turns out it has to still be diagonalizable. It's just topologically a next sum of copies of CP2, or all of CP2 bars, or all CP2s. Yeah, good question.
So are there examples where you have the same homeotype, but the dimension of the moduli space of the Einstein matrix is different for two, like it's positive and it's different for two nucleotypes?
I feel relatively confident that does happen, but so the tricky part is, I gave you examples where the moduli space is actually connected. So one thing that a priori could happen is you could have many connected components and they could have different dimensions. In fact, in the higher dimensional cases, I mentioned, like on odd-dimensional spheres, different connected components have different dimensions, and it turns out that actually, starting in dimension 7, in these special Einstein metrics on the 7th sphere, even the Sasaki Einstein ones, the dimension of certain components of the moduli space gets arbitrarily large. So as you change from component to component, they get bigger and bigger indefinitely. Whereas one hopes that, that in dimension 4, there are many circumstances where one hopes that the phenomenon that I explained, where the moduli space is certainly connected for many interesting examples. We don't know that that's always true. And it definitely, what we do know is that there are certain examples where to get something connected, you also have to include some degenerate Einstein metrics. So the story can be, if you're hoping for any kind of theorem that would say, in general, the moduli spaces should be connected, well, if you interpret it in a naive way, it's not going to be true. But it's if you tweak the definition, it's still possible that that might be a general phenomenon. It would involve anything like that would involve having to include some singular limits, or Orbifold limits, and then that can then be where the singularity can then be deformed away in more than one way. It's a subtle question, very interesting, and I hope that some people in the audience will want to work on this. So, yeah, thanks. That's a good question. Any other questions that people want to ask publicly? And obviously, if you want to just come down and ask privately, that's fine too. Soit en français, soit en anglais. All right, so what we call it a day, and I hope to see most of you back next Tuesday, or at least some of you back next Tuesday, next Thursday.